Hello, and thank you for joining us for today's webinar, Thermoplastics, a Solid Choice for 3D Printing. My name is Sharon Steinhoff-Smith with Stratasys, and I'll be your host for today's event. For those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from 3D CAD files. Using our patented fused deposition modeling technology, our Dimension 3D printers and Fortis 3D production systems are the most widely used additive manufacturing systems in the world. We also operate Red Eye On Demand, an online rapid prototyping and digital manufacturing service. In today's webinar, you'll learn how to choose the right material for your 3D printing project. The majority of today's consumer products and many commercial ones are composed of thermoplastics. When designing a new product, you can best predict its end performance by prototyping with a material as similar to the final product as possible. That's why 3D printing with thermoplastics offers a wise choice. Now I'd like to welcome our speaker for today, Fred Fisher. Fred has more than a decade of experience in additive manufacturing in roles as product manager, applications engineer, and his current position as director of business development for materials. Fred is a frequent speaker at domestic and international events related to prototyping and digital manufacturing. Fred?
All right, thank you, Sharon. As Sharon mentioned, one of my responsibilities at Stratasys today is to really manage the portfolio of thermoplastics that we have available on our technology. So what I'd like to do is to talk and spend a little bit of time today talking very high level about FDM technology, about thermoplastics and in general, and then talk about the 9 thermoplastics that are available in our material portfolio, and try to give an understanding of what makes each of those materials unique so that when engineers are trying to determine if FDM technology, thermoplastics, and then specifically which thermoplastic is best suited to meet their manufacturing or their project needs. Now, as Sharon mentioned, one of the things that happen is design engineers approach a project. One of the things that they're always constantly considering is what is the final material in which they're going to manufacture their product. And thermoplastics are one of the most common materials used to manufacture components of all kinds of different components. Having access to thermoplastics throughout the entire product development cycle really allows engineers to mimic the end product performance, not just at the final product stage, but all the way through the entire development continuum. And having that at the concept model stage, the functional prototype stage, and so on, really allows them to visualize and to feel their design throughout that process and make design changes earlier. As we mentioned, FDM technology is one of a number of additive manufacturing technologies available in the marketplace today, and thermoplastics are really what make us unique. Today, we build parts in our systems by taking thermoplastic material and building that part layer by layer, or as the name suggests, adding layer on top of layer on top of layer until you get your completed part. Since we build in thermoplastic materials, our parts can be used not just for concept models and early on in the product development cycle, but they can be used throughout the entire product development cycle in functional prototyping and actually move from just the design engineering department, but also onto the manufacturing floor, and in some cases even be used as the end products that go out to the consumer of the product itself. So thermoplastics really are the key enabler with our technology to make that happen. Now, as we talked about before with thermoplastics, the key thing with our technology and thermoplastics are the fact that we deliver the material and our technology in a clean, safe package, right? This allows our systems and our technology to be used not just in the office, but it's also robust enough to be used out on the manufacturing floor. So it's really versatile in that sense. The output from our system, since it's thermoplastics, is very durable. We'll talk about the variety of plastics in a moment, but we have plastics that are well suited for concept models, all the way up through really high performance functional prototyping applications. In addition to that, since our materials and our parts are made out of thermoplastics, the parts tend to be stable over time. So there aren't the same sensitivities to exposure to things such as UV light, humidity, heat, and pressure as other technologies may have. So it makes the technology or our products capable, again, of being used not just as concept models, but throughout that entire product development continuum. So FDM isn't necessarily unique in providing any one of these different characteristics, but what makes us unique is the low-cost package that we deliver that delivers all three of these bundled together in a simple package to the design engineer. Again, that can be used not just in an office setting for design engineers, but it's also robust enough to be used out on the manufacturing floor as a manufacturing solution as well. Now, how do you actually choose whether thermoplastic materials or really specifically which material is best suited for your needs? The first thing, of course, that we typically recommend is for an engineer to understand what is their application, right? What do they need this particular part to do? What are the performance or the environmental exposures that the part may have in terms of mechanical pressure, thermal, maybe chemical resistance? That generally, those three categories generally tend to drive which material is best suited for the application. And again, our materials are, again, well suited not just for concept models that get used in the design engineering department, but really all about the functionality of the product as well. So since we're mimicking the end product by using the same thermoplastic materials, engineers can test not just form and fit of whether a part fits together or it has the right form, but also whether it has the correct functional capabilities to meet the application needs. And we'll talk about a few success stories or users who do just that with some of the materials. Now, all of our materials aren't available on all of our systems, so one of the other important considerations is depending upon what material you have may dictate which system or FDM system is best suited for your need as well. In many cases, color is also an option. We'll talk about color in a moment and the value that brings. But in general, a number of our materials are available in a standard kind of rainbow of colors, if you would, that allow engineers to visually dictate different components inside of a design, as well as potentially indicate what stage in the development cycle a particular part or prototype is in. And again, as we've referenced before, since we're building in thermoplastic parts, this isn't just a technology for design engineers anymore. Our technology, as well as just general additive manufacturing technologies, have improved over the last 5 years and are now being used not just by design engineers, but are also robust enough, the output is robust enough and accurate enough that it can be used by manufacturing engineers as well for things such as jigs and fixtures out on the manufacturing floor, as well as in some cases where low volume or high complexity parts are the design characteristic. They can also be used as the actual end product itself. So let's talk a little bit about the 9 materials in our product portfolio. And the first material we'll talk about is really our best-selling material, and that's ABS material. And why ABS material is our best seller? Number one, it's available on all of our product platforms. So every system that we have has a flavor of ABS that can run on it. In addition to that, ABS is one of the most commonly injection molded materials in the manufacturing space as well. Now, we brand up our ABS materials in with two different brand names, ABS Plus and ABS M30. The material itself in either a canister or cartridge actually happens to be identical, but what happens as a result of the two different families of technology or systems that we have, 3D printers, which are best suited for concept modeling and maybe light-duty functional prototyping, and then our 3D production systems, which have advanced electromechanical components as well as software that drive the system, really tend to produce a part that has higher performance characteristics. And this would be an example of that, where it's the same material going in, the same ABS material going in, but it's a different part coming out. The parts from a 3D production system or in ABS M30 tend to be mechanically superior, anywhere from 5 to about 20% superior over an ABS Plus part. So again, both of these technologies can produce parts that are very well suited for concept modeling, and the 3D production systems parts from the 3D production systems tend to produce parts that have higher performance capabilities, if you would. Now, with that, with the ABS materials, as the image shows, ABS is one of those materials that comes in a variety of colors. And as we mentioned before, engineers tend to gravitate for colors for a couple reasons. One, potentially, is to create assembly components that kind of can highlight or identify and differentiate different components inside the assembly. Dana Axle would be an example of one of our end users who creates assemblies, and they create different components inside that assembly. So when they bring a concept model to the OEM engine or the OEM vehicle manufacturer, they can highlight those different components inside that concept model design that they bring to the OEM supplier. In addition to that, as I mentioned earlier, color sometimes can be used to identify what stage in the product development cycle a component is in. So some companies tend to use, let's say, blue material as concept models. Yellow parts tend to be parts that are in the detailed drawing stage, and let's say blue parts would be, or green parts might be, the final design evaluation stage. So colors can also do that. In addition to that, with ABS material, we have really kind of no-touch finishing options. With additive manufacturing technologies and FDM technologies specifically, since we're building in an additive fashion, we not only need the model material or the material that makes up the end product itself, but then also a temporary support structure in which we sometimes can build upon if there are overhangs or internal cavities that need to be temporarily supported. In the case of the ABS family of thermoplastic materials, we have all soluble support materials, meaning those supports can be removed hands-free or labor-free. There's no touch labor that's required to manually remove those supports. It gives you the convenience of automatically dissolving those supports in a detergent-based bath. In addition to that, the ABS family of thermoplastics tend to be the easiest thermoplastics to finish, whether you want to hand sand, fill and paint the particular parts to mimic the end product, or in our case, we actually have a finishing touch station that works very well with our ABS family of thermoplastics that then can improve that surface finish for those applications that really dictate or require a high surface finish to it. So such as, let's say, tooling masters for investment casting, RTV tooling, or again, in the case where you want to paint the part to look like the end product. The next material we'll talk about is ABS M30I. And ABS M30I is a different flavor or derivative of ABS M30. And what makes ABS M30I unique is the fact that it's a biocompatible thermoplastic. So that means it's passed or has certification for ISO 10993 and USP Class 6. Those two classifications and the biocompatibility make it a really well-suited material for medical applications or parts that need to go into the operating room or operating theater, as well as food and pharmaceutical packaging applications as well. What can happen with this biocompatible material is it can be sterilized through a variety of different methods. In the case of ABS M30I, gamma ray and the ETO sterilization tend to be the two most common methods to ensure that that part is indeed sterile to go into either of those application environments, the medical, pharmaceutical, and food packaging applications. The example that you see on the screen is an example of a particular part that tends to be used, or ABS M30 is used for. This is a concept model that can help a surgical team communicate amongst themselves and plan the surgery, as well as communicate to the patient before the surgery happens, as well as the fact that since this is ABS M30I, that communication model can actually be brought into the operating theater as well, or the operating room, and used as a communication tool or an aid in the surgery as the surgeons go through the surgery. That communication models in the operating theater tend to reduce the time that the surgeries take, or reduce the time the patient's under anesthesia, and it also improves the success rate of the surgery as well. So again, a big benefit to bring the part into the operating theater, and the unique characteristics of the biocompatibility of ABS M30 really enables those particular applications. The next material we'll talk about is the last material in our ABS thermoplastic family. This is ABS-I. And ABS-I, as the image indicates, is really known for its translucent material properties. It comes today in three different colors: red, amber, and natural, the natural being the sort of translucent or most clear material. And we've logically chose these three colors because one of the biggest applications is the automotive lens applications. Automotive companies or automotive suppliers supplying components or lenses to the automotive industry, they can mimic the translucency of a typical automotive tail lens with the ABSi material. In addition to that, there are other applications where translucency is a requirement as well. An application using that might be, for instance, companies designing intake manifolds that want to do testing on that intake manifold. They can build it in the translucent ABSi. They can put that design or that prototype, that functional prototype, on a test stand, put particles in the liquid that passes through the intake manifold, and then test or visually measure and monitor with high-speed cameras the different designs, and then choose an intake manifold design that best suits their needs. So an example of where translucency is beneficial in, I guess in that case, the functional model stage. The next material we'll talk about is polycarbonate material, and this is the next family of materials. And like the ABS family of materials, the polycarbonate materials tend to be some of the most injection molded and machined thermoplastics used in industry. PC is generally chosen both in traditional manufacturing as well as in FDM, where there are higher performance requirements on that part, specifically tensile strength and heat deflection being the two most common mechanical characteristics that drive an engineer to choose polycarbonate material. ABS materials, as an example, have heat deflections around 100 degrees Celsius. Polycarbonate ups that by about 50 degrees Celsius, or brings it to approximately 150 degrees Celsius for the heat deflection temperature. So again, if the functional prototype or the end product itself needs to survive a higher mechanical environment or a higher heat stress environment, PC can be a good choice in that particular application. An example of an end user using polycarbonate material would be Bradken. Bradken is a sand casting manufacturing company or sand casting service company to the heavy industry in Australia. And Bradken chose polycarbonate material to create the match plates for sand casting. So the plates that actually get exposed to the very high compressive stresses of the green sand casting application, as well as some of the steam and heat exposure as well. And in their case, PC material was a great solution because they needed a part that could survive, or really they needed to create match plates that could survive that high compressional forces and some of the steam and other exposures that the green sand application provides. So again, polycarbonate material was a great solution for them for that very reason. The next material we'll talk about is PC ABS, and as the name suggests, PC ABS is a blend of polycarbonate and ABS plastics. And again, this is another material that's very commonly used in the injection molding world for consumer electronics, business machines, and or hand tools as well, really because it blends kind of the best characteristics of polycarbonate material and the best characteristics of ABS material. For us, this material tends to be known for it's one of the most high impact strength materials that we have in our portfolio. An example of an end user using this would be Skill Bosch Tools. They use PC ABS to model or to create functional not just concept models, but functional prototypes of all of their hand tools. And they then take those functional prototypes, they use them both internally as well as they give them externally to construction workers and put them through really kind of the rigors and the pace and the environment that a typical hand tool will go through. So the PC ABS is the end material they would produce that part in, and it also allows them to create a functional prototype to get real field testing feedback from the professionals who would actually use their product. In addition to the high impact characteristics of PC ABS, the other thing that it does is it is one of the materials that models extraordinarily well to give us high feature detail and surface finish. Now, one of the things with our technology that drives high feature detail and surface finish is the layer height, or the height of which each of those layers that we build is. With PC ABS, as well as our ABS family of thermoplastics, we can build our smallest layer thickness, about 5/1000 of an inch or 0.127 millimeter slice thickness, and that tends to then produce parts that are not only have good feature detail and surface finish, but also then have sort of improved mechanical characteristics as opposed to ABS. So another material that's well suited for feature detail and surface definition. And last but not least, like the ABS family of thermoplastics, soluble supports are available with the PC-ABS, so you get the convenience of hands-free support removal with PC-ABS as well. The next material we'll talk about is another polycarbonate-based material, and it's somewhat similar in the sense as well as ABS M30I in the sense that it's also biocompatible, so it passes the same or has the same certifications, ISO 10993 and USP Class 6, so making it well-suited for those very same applications, the medical, pharmaceutical, and food and processing or packaging industries. It can be sterilized through the same methods, gamma ray and ETO sterilization methods, but the big benefit that polycarbonate brings in this particular application, of course, is the improved mechanical and thermal performance of this particular part. So those applications that require mechanical and thermal characteristics above and beyond ABS in the medical or food and pharmaceutical packaging industry, PC-ABS can be a good solution. An example of some end users using this are some of the end users in the packaging industry creating blow molds for bottles, where those molds are exposed to relatively high heat from the blow molding process, as well as they want the ability to have that tool sterilized so those products can be used in a variety of different applications, really specifically in the pharmaceutical applications. So again, PC-ISO, all about the biocompatibility with improved mechanical and thermal performance above and beyond ABS M30I. The next material, ULTEM 9085, is a material from SABIC, and SABIC has manufactured this advanced thermoplastic material really geared for kind of the commercial transportation industry, or maybe even specifically the aerospace industry. Why the aerospace industry really desires and likes this material, chooses ULTEM 9085, is really its high strength to weight characteristics, as well as the FST certification. So the high strength to weight ratio allows aerospace design engineers, or for that matter, anybody in the commercial transportation industry, to design weight out of their product. And again, in the aerospace industry, that's really a critical element to their design components, is to take weight out of the vehicles, which of course translates into efficiency of the vehicle itself. In addition to the high strength to weight ratio, ULTEM 9085 has the FST certification, or Flame, Smoke, and Toxicity certification. And in general, what that really means is if this product or a product manufactured in ULTEM 9085 were to come in contact with a flame, the smoke and toxicity given off from this particular component burning is low enough that would be minimally harmful to a passenger inside that commercial vehicle or that airplane, that train, that boat, whatever may have that requirement. In addition to being very well suited for the aerospace industry, ULTEM 9085 tends to be one of the most mechanically well-rounded materials that we have in our portfolio today. So what does that mean? If you kind of look side by side at the mechanical characteristics, and for that matter, thermal and chemical characteristics of this particular material, ULTEM 9085 is either at the top or nearly at the top in almost all of those categories. So it's a very broadly or well-rounded, mechanically superior material that, again, works very well for aerospace, high-performance automotive, commercial transportation application. But in addition to that, any application that really requires a very broad mechanical superior output, ULTEM 9085 is an excellent choice for those particular applications. And the last material we'll talk about is, again, an advanced thermoplastic material, polyphenol sulfone. The polyphenol sulfone, or sometimes abbreviated as PPSF or PPSU, it really was designed for two different applications. Applications for the automotive industry under the hood. This material has the highest heat deflection, around nearly 190 degrees Celsius heat deflection. In addition to that, Polycarbonate cell phone is not only thermally resistant, but it's also a very mechanically superior part. In addition to that, it's also chemically resistant. So generally, materials such as petroleum-based materials, such as gasoline, oil, antifreeze, other materials that can be found sometimes under the hood or in other application environments, PPSF can withstand those particular environments. Now, in addition to being very well suited to be under the hood, it also, like ABS M30I and PCISO, can be used in the lab, right? It can go into the operating room or into other environments where sterilization is required. Since PPSF has a higher heat deflection, it can be sterilized not just with gamma ray and ETO sterilization, but we can also use other sterilization techniques like autoclave, steam autoclave as an example, that really expose that particular part in the sterilization process to higher heats. Now, an example, again, of a company, and the actual image that you see on the screen here of a company using PPSF is Parker Hannifin. And Parker Hannifin, about 10 years ago in the United States, the United States changed emissions controls on diesel engines. Diesel engines had to burn cleaner. And as a result, the OEM engine suppliers had to determine how to reduce to make their engines burn cleaner. And they turned to Parker Hannifin to design what's called a diesel coalescer, which is what you see on the screen there. And what the diesel coalescer does is it essentially filters out unburned soot and other unburned diesel fuel and other pollutants or contaminants that normally would flow out the exhaust pipe. It reintroduces this into this diesel coalescer that filters those components out, introduces them back into the combustion chamber where they're burned, and then thus the emissions are reduced. Parker Hannifin was faced to prove to the engine supplier they were dealing with that their diesel coalescer indeed either met or exceeded these new emission standards, and they turned to FDM technology and PPSF to create that functional prototype that could be used not just to test the form and the fit of the design, but also to be bolted on the engine during the testing phase. They used this particular part and ran it on an engine stand for over 80 hours. It withstood the temperatures and the chemicals, the diesel and other diesel, soot, and other chemicals that the product was exposed to, that normally other thermoplastic parts really wouldn't be capable of, or where maybe, let's say, potentially a CNC machine metal part would have been required to create that prototype. So, again, an example where a very high requirement application drove the need for an advanced thermoplastic, in this case PPSF, for its not only mechanical superiority, but its high heat deflection and chemical resistance as well. So that's a short look at why thermoplastics are important to design engineers. And again, as we mentioned earlier, thermoplastics, or engineers gravitate to using thermoplastics earlier and earlier in the product development cycle because it helps them mimic the end product performance earlier on, find those design changes or mimic that product performance and invalidate whether their product meets their needs. As we mentioned, we have 9 thermoplastics that are available in our product portfolio today, or in our material portfolio today. What this allows engineers to do is really to choose the material that is best suited for their application, and they can vary that based upon the mechanical characteristics of that material and or the chemical and thermal resistance that's required for the application. So again, we have a broad range that really covers materials that are used really well for not just concept modeling, light-duty functional prototyping, but also into applications that we can use on the manufacturing floor, such as manufacturing tools and even the end-use products themselves. So that's a very brief look at the materials in our portfolio, and with that, I'll turn it back to Sharon.
Thank you, Fred. In just a minute, we'll take any questions that you may have. If you think of a question in the meantime, be sure to submit it through the chat panel. I also want to let you know that after our event today, you can find this recording, request a sample part, and download other relevant materials at www.stratasys.com/materials_webinar. Okay, looks like during the presentation a couple of questions have come in that we have some time to take now. So here's a question from Martin, who asks, how does the strength of one of your thermoplastic parts compare to the strength of an injection molded part?
Well, excellent question, Martin. In general, the strength of a part off of an FDM system in comparison to injection molding really it varies on a couple different considerations, specifically the geometry of the part and the material that you're actually producing that part in. For our ABS materials, we tend to be in the neighborhood of 80 to 85% of the strength of an injection molded part. So the parts coming out of an FDM system in ABS material are very close to the same strength of a part in injection molding. Again, that can vary based upon geometry. As you get into some of the other thermoplastic materials, ULTEM, 9085, PPSF, we're generally in the range of about 65 to, again, about 85%. So there's a little broader range in some of those other materials. So it's really about the material that you're building in and the geometry itself, but we tend to be in that kind of 80-85% range of injection molding strength, which tends to, again, be well enough for engineers to mimic or indicate whether their product will meet the end performance requirements or not.
Great, thanks. Here's another question. This one's from Tony. Are there any other 3D printing processes besides FDM that use thermoplastics?
Well, good question, Tony. As we mentioned in the presentation earlier, the unique thing that makes FDM specifically desired by engineers is the fact that we build in real thermoplastic materials. Indeed, there are other technologies out there that can produce parts that have mechanical properties that approach or are very similar to the FDM output mechanical properties. But what makes FDM unique is the fact that we are really building in real thermoplastic materials, right? The same thermoplastics that go into an injection molding machine are the same thermoplastics that go into an FDM system. And as a result, we can mimic not just the mechanical characteristics of that part, but we really have the stability over time as well, right? So the same stability that you'd find in an injection molded part, you find in an output from an FDM system. So it's not as susceptible as some of the other technologies may be to heat, ultraviolet light, moisture, or pressure over time. So that's what really makes our technology unique and different, is the fact that we do build in real thermoplastic materials.
Great, thanks. Another question is from Simon. Are laser-sintered plastic parts stronger than FDM plastic parts?
Well, good question, Simon. Again, laser sintering, of course, one of the key characteristics that laser sintering output has, of course, is its robust output, similar to FDM in that sense. How FDM differentiates from laser sintering isn't so much in the mechanical characteristics of the output, but really in the process itself. As we sort of alluded to briefly in the beginning of the presentation, FDM technology delivers output all in a package that's very clean and inexpensive and easy for an operator or a series of operators to run. SLS doesn't have necessarily those same characteristics. So as a result, FDM technology can be put into different environments, right? An FDM system, a 3D printer as an example, can be put right on the desktop of an engineer's, right on the desk of an engineer, because it's simple, it's clean, it's quiet, it's easy to run. It's, of course, robust enough to also be used out on the manufacturing floor as well. So although we don't necessarily differ in terms of the mechanical strength of the output, it's really the process, I think, that's the key differentiator between SLS and FDM. And as someone evaluating bringing a system in-house, you have to understand whether you do or don't want to, what you want to be exposed to, right?
Looks like we have time for one more question. Karen is wondering, how good is the accuracy of FDM parts?
Well, again, another great question, Karen. Accuracy for FDM output is again, one of the cornerstones of our technology. The fact that our parts are durable and stable over time. So we have systems, our highest performance systems can produce parts that have accuracies that are approximately plus or minus 3.5 thousandths of an inch. So we are one of the most accurate technologies, not only initially out of the system, but over time our parts hold their shape and are stable in typical office and typical environments where the part is out into the field. So it's not just about the accuracy coming out of the system, which our technology excels at, it's also accuracy over time, which thermoplastics, of course, are very well suited for.
Thank you, Fred. And thank you all for your questions. If we didn't get to yours live on the call, we will follow up with you via email. We'd like to thank each of you for your attention during the presentation, and now I'll turn it over to our operator who will close out our session.